I think it's recording. Hello everyone, my name is Dr. Suraj Jaiswal and welcome to the first tutorial of the course entitled Simulation of a Mechatronic Machine. In today's tutorial, we will go through the basics of Simscape Multibody and then we will see that how we can model a double pendulum. In this course, we will be using Matlab version 2023A. As a sneak peek, you can already see a double pendulum where the trajectory of the end point of the second body is being computed. So these are the list of contents that we will be covering in today's tutorial. First, we will see what is Simscape Multibody all about. Then we will see some user interface and basic components. Then we will see what are the things required to model a double pendulum and how we can model it. And finally, we will see some tests and results. So what is Simscape Multibody all about? Simscape Multibody provides you with a simulation package with which you can model any mechanical system, be it a robot, be it a heavy machinery, be it vehicle, construction equipment, aircraft, whatever you like, you can model it using this particular package. In this particular package, basically any system can be represented as a multi-body system where you can have a number of bodies, joints, constraints, and force elements between them. Simscape Multibody formulates and solves the equation of motion of the entire system, and you can import your own CAD objects if you want to have any complicated geometry there. The good point about this particular software package is that you can visualize the 3D animation of your system without much effort, and it's automatically generated. Very important point that you can integrate systems of other physical nature such as hydraulics, electrical systems, pneumatic systems along with your mechanical systems using this Simscape multibody. So let's get started with the user interface and basic components. Before that, I would like you guys to go to the search window on your system and type for Matlab. I'm assuming that you have Matlab 2023 a version with you. So you can either search it from your computer or just search it on the from the shortcut on the desktop. There would be a desktop icon for Matlab. It will take a while to open. Okay, so the Matlab window is open. If you are new to this software MATLAB at the first place, I'll briefly explain you. So this is the command window where you can type your command. This space is mainly used for workspace. It's at the moment it's empty. This is your current folder, what you have selected, and this is the path to the correct folder, current folder. What I want you to do is go to browse for folder and select the folder where you would like to save your file, be it download, be it C drive, wherever you like, and just select the folder. I have already pre-selected my folder. Okay. Now in the command window, you need to write sm new. So Simscape multibody new. Either you can write this command and press enter, or you can write sm new and in bracket under this inverted commas you can write the name of the model name. So it will open a file with the name that you provide here. Let me use simple pendulum YouTube. Okay, and then I press enter. Now you can see the status here. It's showing busy. It's because it's trying to open a Simulink window. So now it's saying starting Simulink. Don't press any other things at the moment because it's still processing the last command that you send in the command window, okay? It's taking more time than usual. But yeah, that's normal. That's very normal. Okay, so now my uh, Simscape multibody file is open. The first and the foremost thing, go to save as, and save your file in the same folder where you just selected this folder over here in the current folder, right? So save it. It will be saved under the same folder. And the name you already provided, if you want to change, it's still possible. And save it as a .slx file. You can the other file formats that's available is .mdl file. Don't Let's not go there. Save it as a .slx file, okay? And then just save it. Now, this is basically a user interface that you will experience every time you open Matlab Simulink, right? Or Simscape Multibody. So very briefly, this is the visual control with the help of which you can zoom in, pan, fit view, and other things you can do. Then over here, you can see there is the status option showing which is ready. So your file is ready to be executed. Then over here it shows like the zoom in percent, how much you have zoomed in into the screen. Okay. So like by just scrolling in and out, you can zoom in and zoom out. Then this variable step auto is basically providing you information about the solver information. Okay, if you press this, you can there is an option view solver setting. So you can even go to the solver setting and change those settings of your solver. Okay. On the top, this is the simulation control where this is the simulation stop time, this is simulation run, and then step forward, step backward. Then there is a library. This is the Explorer bar. Okay, so it will show you if you have any other subcomponents within this model, you can simply go in. This is the Explorer bar. This is library browser. Library browser contains certain ready-made component blocks that we will be using. So either you can access the library browser from here, or you can access the library browser using this shortcut here, which is Simscape Multibody Library. Okay. So this text is self-explanatory if you read it, but just for your information that you can access the same library from here or here. Okay. Now there are some basic components here which will be there in every file. So these three components will be required in every model that we are going to do. First is the solver configuration. In order to solve the entire system, we need some kind of a solver, right? And so this is basically about the configuration of that solver. Then we need a world frame. So basically a reference surface or a reference ground where we will where we will have our origin or the global reference coordinate system or the inertial reference system, whatever you name it. Then we will have mechanism configuration. So basically the configuration of the mechanism as the name suggests itself. Then we have these components. And by the way, if for you these names are not coming, you can just select all of it, go to format and go to name on. So auto name, name on, name off. So if you name off, the name will be disappearing. If you name on, all the names will be coming. So if it's not coming for you, you can just change it from there. Then using this brick solid, you can model your bodies. So brick solid will basically help you to model rectangular shaped bodies, and then you can search for joints as well, which I will show you later. Now this rigid transform is basically there to help you convert from one coordinate system in space to another coordinate system in space. Okay. uh, Whether you can just translate this coordinate system or rotate it or do a combination of it. So this rigid transform is exactly converting from one coordinate system to another, basically any kind of transformation. Then we have Simulink physical system converter and physical system Simulink converter. So this is just to convert the signal from the Simulink signal to the physical system signal or the other way around. And scope is there just to view these signals in a graphical form. Okay. And over here there is data inspector. Of course, data inspector can help you to view the same plots, and using data inspector you can even save your plot or generate compare different results and so on and so forth. So moving back to the uh, presentation, I think I have covered everything in here. Yeah, let's move on. So now we need to model a double pendulum. And what are the things required for a double pendulum? Don't look at the slide, but try to just think in your mind. When I say double pendulum, as the name suggests, double pendulum. So clearly, uh, I can guess that we need two bodies, correct? Now, when we need two bodies, both the bodies should be connected to each other, right? And they should also be connected, the entire system should also be connected to some reference surface. So at least we need two joints in there. At the moment I'm not telling you what kind of joint, okay, just two bodies and two joints. Now we spoke about a reference ground or a reference surface, so we need a ground for that. Okay, now when we have ground, you need a particular point on the ground. Basically, you need your origin, the global origin or the global coordinate system or the inertial reference system with respect to which you will start modeling your system. So you need that as well. And then you need an external force, gravity, so that your double pendulum can execute the oscillation, right? So these are the five requirements what we would like to model. So this is illustration of a double pendulum. What I would do, I would just take a screenshot of this particular slide so that I'm able to explain you few things with time. Okay. Now, when you see this double pendulum, let's go to individual body, which is this body, red body, and the green body. Okay. Now, think very carefully that in the course you might be taught about two-dimensional space, but Simscape Multibody helps you to model it in three-dimensional space. Okay. So now I will just explain you. Let's talk about that. We are just trying to model just one body and uh, one joint. So we are just focusing on the simple pendulum. Okay, because when we model just a simple pendulum, we can just extend that to make it a double pendulum. We can just use the copy paste technique what we engineers love to do, right? So we can just make a simple pendulum and then just extend it. So focusing on simple pendulum, suppose this is a simple pendulum which is like connected. So this is the ground and it's connected here like this, and it's in two dimensional, right? So this plane is this surface is basically representing two dimensions. And if I model this simple pendulum in two dimensions, then what will happen? Like, it will just do this reciprocating motion in this plane, correct? I hope you're able to see. Okay. Now think about, if you just need to define a body in two dimension, forget about the joint. How many coordinates do you need? So this body can translate along the x, This body can translate along the y, and this body can rotate on this surface, right? So in order to define any body in two dimension, you need three coordinates. And by the way, we are considering horizontal to be the x-axis, vertical to be the y-axis. Okay. And the one coming out of the plane is the z-axis. So in order to define this body, you need three coordinates: 1, 2, and 3. Now, if you have a revolute joint here, which is okay, let me take another one. So if you have a revolute joint here and you want to connect it with this point on the top, what will happen? This revolute joint will constrain this point on the body to be always here. It will not translate in the x direction or on the y direction, but it can rotate in this in about the z axis, right? Like a simple pendulum. So this revolute joint is offering how many constraints here? It's offering two constraint equation. So body in general is defined using three coordinates, but two coordinates are being constrained by this revolute joint. So how much is the degree of freedom? It's 1. What does degree of freedom mean? Degree of freedom mean that the freedom with which the body can have execute certain motion. So over here, the body can only do motion in this form. So the degree of freedom itself from the physical system, it's 1, right? That's what we can already see without the mathematics even. Now let's assume that now the things are in 3D and not 2D. So let's remove this 2D surface, and now this this particular body is in 3 dimension. How many coordinates do you need in order to define this body? 6, because it can translate along x, it can translate along y, it can translate about z. Then it can also rotate about x, it can also rotate about y, and it can also rotate about z. So 6 coordinates you need in order to define a free falling body in space. Now, the moment I say let's constrain this system over here so that it acts like a like a simple pendulum. So I'm constraining this point here, and now what I'm trying to do is this will execute like an oscillation motion, correct? This will have a motion like this in space in 3D. Now, if we put a revolute joint here, we know that revolute joint can offer can help to execute this particular body only in this format, right? So now thinking about this point on this body, what is the revolute joint doing here? It's constraining this point such that this point cannot translate in x, cannot translate in y, cannot translate in z, correct? Also, it cannot rotate about x, it cannot rotate about z, but it can rotate about, sorry, it cannot rotate about y, but it can rotate about z. So this particular revolute joint in 3 dimension is imposing 5 constraint equations. Understand this very carefully. So now the degree of freedom of this system is still 1, because 6 coordinates required to define a body, and then revolute joint is imposing 5 constraints. So degree of freedom is 6 minus 5 is 1. And also you can already guess that from the physicality of it, that it can only execute a motion in this format, in this way. So there's only one kind of motion possible, so of course the degree of freedom is 1, correct? Okay, let me get the other body as well now. Okay, now if you have understood this very carefully, let's go back to the modeling. Now suppose this is the body that we are trying to model, and we will model it in such a way that x is horizontal, y is vertical, and the z is coming out of the plane, correct? Now, in every body, there needs to be a body coordinate system, correct? Body reference coordinate system, or the points on the body, the reference points with respect to which you will model the rest of the of the system. So if I see this particular body in this particular example, we clearly know that we need a reference point here. I hope you are able to see, because with uh, uh, this will be connected to the revolute joint, and we also need a reference point here, so on two ends of the body. So what we need to do, we need to define a reference frame here. Sorry about the bad drawing. And we need a reference point here. So two reference point, which is also called reference frames here. Okay. Now this is how the body is. This is in the body coordinate system. This is x, this is y, and z is coming out of the plane. Correct? Now, if you see this global x, and this body coordinate system x, they are at a certain angle with respect to each other, correct? And it's in the counterclockwise direction. So we also need to take care in the modeling that suppose if this is 30-degree, let's say, and it's in counterclockwise direction, so it's negative. Always, sorry, yeah, counterclockwise direction is considered positive and clockwise direction is considered negative. So this is clockwise direction, correct? So this is minus 30-degree. Or you can have defined it in the counterclockwise direction, and whatever this angle is, 330-degree, it would mean the same thing. So it's up to you how you want to model it. But if you have understood this carefully, let's go ahead and model our system. Half the job is done, that understanding the system itself at the first place, and the rest of the tutorial is just simple execution of instructions. Okay, now let's go back to our simulation of our Simscape Multibody file. So first and foremost, go to mechanism configuration, and in mechanism configuration, by default Simscape Multibody assumes that x is horizontal, z is vertical, and y is going into the plane. This is what Simscape Multibody does by default. I don't know why. But what I would like us to do, for simplification purpose, we will consider x to be horizontal, y to be vertical, and z coming out of the plane. Okay. So I want you to change the value of gravity, which is minus 9.18, from minus z to minus y, because this is x, y, and z coordinate, and press enter. Okay, it's already auto apply here, so you can simply close this window. And in order to open it, you can double click and open it, correct? Earlier, it used to be that you can right click and do there used to be an open option here, but it's not there anymore. So just for your information. Okay, now how to access the library in order to in order to model certain components. By default, you already have these components, okay, which is good. What I would like you to do is just select all of them, right click, and say comment out. So they are still there, but not participating in the simulation at all because they are commented. Okay. Okay, in order to search any component, you can either search from the Simscape multibody library. So for example, suppose I want to have brick solid. Okay, you can go to Simscape multibody library by simply clicking in. It will take you to Simscape multibody, and then you can see different body elements and so on and so forth. So under body elements, you can find brick solid and other kinds of bodies as well. So you can simply left click and drag onto the screen. It will come. Okay, I'm just deleting it. Or the alternative way, if you don't want to do it from here, you can search for the library browser here, and then it will show you a list like this. Then you can scroll down, go to Simscape. Then under Simscape, go to Multibody, and you can have the same things over here. For example, body elements. You see the same things are over here. So you can select a brick solid and drag and drop. So it will give you the same block here. So it's very simple. The third way of finding any component block is by double clicking anywhere on the screen and just type the name if you already know the name of the block. So brick solid. Okay. So these are the three ways of finding any component block. Of course, you can use the shortcut, but as an engineer, you should know where exactly this component block is located in the library browser. So it's very important for you as well. Let's delete it. Okay, one important aspect that I have explained to you here, that either you can so this is not required for you at the moment, but just it's good to know. Either these parameters under any component block, either you can assign it directly the way it's already there by putting in the number in the component block, or they can be loaded as a variable from the Matlab workspace. What I mean by that, for example, under mechanism configuration, instead of providing a number, you assign a variable here. Let's say a variable -g. And then in Matlab, if you go to the Matlab, the workspace at the moment is empty here. You can just define a variable g with some value here that will be assigned to that component block. So if you want to control certain parameters, you can simply change it in your M file in Matlab, and everything will be changed in your simulation model. We don't need to do that, but just for your information. Okay. Now remember our requirements. We need a ground, we need gravity, we need a global coordinate system, we need bodies, and we need joints. That's what our requirement is here, right? Correct. So we took care of the gravity already. Now, world frame, if you double click, you can already read these descriptions for every component block. It will help you much better than my explanation. So if you like, please go ahead and read them. World frame already takes care of the ground and the global coordinate system or the inertial coordinate system. So you don't need to do anything in that regard. So by default, three things are already taken care of, which is ground, gravity, and inertial coordinate system, right? All we need to do is model bodies and joints. So let's see how we can do that. Now, in order to model bodies, let's go back to our file. And by the way, keep saving it. This star mark over here shows that it's not saved. So I want to save this file. So I saved it already. Now, I already have the brick solid here. If suppose I just delete it by just selecting and either right click, and there will be this option remove or delete. Ah, it's not there. Okay. So you can simply right click or delete, or and then search the same block again. Or if it's already in the uh, if it's already in this format, you can right click and uncomment. It will show you like this. So we will use brick solid in order to define our first body for the simple pendulum. So double click this particular block. You can read the description, by the way. Now, very briefly, this is the visualization of your body. This is the visualization window. This is the parameter description window where you can describe this particular geometric feature, and this is the visual control on the top. The first and the foremost thing I would like you to do whenever you model, this is a good modeling practice. You see by default Z is in the vertical axis. I want you to press the center cursor and rotate this body so that now Y is vertical. And then use this pan option here. So either you can select this pan view and move, or you can, I think, press shift and center cursor and you can do the pan view. So just a shortcut. I have provided the shortcuts in my slides, which I will show you. So now you can, you know that, and I will try to use as less shortcut as possible so that you can see what's happening on the screen by using these visual controls here. Okay. So let's select this select option. So now my Y is vertical, X is horizontal, and Z is coming out of the plane. And I want to model a body like this. Okay. So actually, let's go to the slide. We would like to see the details. So I want the dimension, and over here the dimensions are X, Y, and Z. And by the way, for your very important information, we will follow one unit throughout this model. So don't mix up with the unit here, okay? Always follow just one unit. Even when defining the gravity, we defined minus 9.181 or something like that. But the unit was meter per second square. So in the dimension also, we will define it in meter. And what's the dimension? Along the x is 0.2, then space 0.04, then space 0.02. Correct? And press enter. Every time you make any changes, it will ask you to update the visualization window. Either you can do it pressing F5, or you can simply update visualization button here. And now you can scroll in to zoom, and now you can see the body the way we would like it to be. And if you press this toggle visibility of frame, you can see there is already a center point here, which is R. Correct? Okay, so things are looking in shape for us. Now go to inertia. We want this body to be we want the inertia to be calculated from geometry. You can select other options as well. And we want it to be based on density only. And we provide the density to be that of steel, so which is 7,800 kilogram per meter cube. Press enter, update the visualization window. Then under derived values, update all the parameters. So basically the mass will be updated, the center of mass will be updated, moment of inertia, product inertia, and the units are also the way we selected it to be. Okay. If you want to update in every step, you can, but sometimes it's annoying. So let me make all the changes and then I will press the update button. Okay. Now under graphics, I want to change the visual property. So I want to change the color of it. Over here, the color is in the format red, green, and blue. I want to make it more red, so I increase the red value from 0.5 to 0.9. Press enter. So this is the new color. And the moment I press the update visualization window, it will update it to be a new color. Correct? Now, we need to define frames. Remember I told you about frames here. So these body coordinate systems are called as frames, or these points are called as frames, right? By default, this port R is already at the center. So if we go back to our file and then show you this, if you uncheck this port R and then press apply, you will see this R is disappearing from here. But if you check this and press apply, this R appears. So this is what it does, checking and checking. Let's update the visualization window again because it will keep notifying us to do that. Okay, now in order to define the new frames or the new reference point on this body, at least we know that we need one on the back surface and we need one on this particular surface, right? So we go to new frame. We can write the frame name here. Then we go to the visualization window and rotate it using the center cursor. Then we simply select this surface. Then we press based on geometric feature and press use selected feature. So centroid of minus x surface is the geometric feature that is selected, and we just press save. So you see now I already have a frame on this surface. Okay. Similar way, and remember y is up in the vertical axis, and the similar pattern is following here. Now let's go ahead and model another frame here. So go to new frame. I'm naming it as F2. Select this surface. Press based on geometric feature. Use selected feature. You don't need to worry about the other options here. You can just save it. But just to briefly tell you, these other options basically helps you to rotate this axis here already. So if you don't want your x to be in this direction, y to be in this direction, and z to be in this direction, you can change and play these orientations with these two frame axes, primary and secondary. We don't want to do it, so let's not go there. So just save it. So now we have our first body ready, correct? And if by mistake you press this isometric view, don't get confused when body is reoriented like this, because you see the orientation itself is changed here. So you need to press the center cursor and rotate the body. This is how our body is going to be arranged in the actual system itself, right? Either you can press apply and then OK, or simply OK, it will save the changes. So you can see now F1 and F2 are here already. As a good practice, what I do is, first of all, I rename the block. Mm, Renaming is very important. It will make your life easy. So I am renaming it as body 1. Okay. Now I'm just re I'm just like changing the shape of this block the way I want it to be, so that it's for my clarity. So at least I know I want this system to be arranged. If you see this one, my F1 is here and F2 is here, correct? So that's how I'm arranging it to be. So F1 is on the top, F2 is at the bottom. Let me remove, I mean, it's already commented out. Let me take out these ones. And also, I'm not a big fan of this particular text, so I just select and delete it just for simplicity. So our first body is ready. If you want, and you realize this particular geometry is quite simple. If you want to have complex shaped bodies, you can read more about them over here, but it's not needed in this particular course. Of course, we will teach that in the advanced course, but it's not needed at the moment. But if you still want to read about them, I will provide the link in the description of this video. Now we need to model joints. Let's go back to our system here. So when I was telling you about joints, we kind of figured it out already that we need revolute joints. So if you already know that what kind of joint you need, it's simple. So we had already done analyzed our system and the requirements very carefully and nicely. So modeling is a piece of cake. So you can either go to the library browser or search directly by double clicking on the screen and search for revolute joint and press this option to show block name. But it's very important for you to know where is the revolute joint. So I will show you that part as well. Go to library browser or using the shortcut that I just deleted. Under Simscape, under Multibody, under joints. So if you go under joints, you can see this revolute joint. You can simply select and drag it onto the screen. But do not get confused with constraints and joints. Even joints are imposing constraints on the system, but over here they are defined it in two different format, because under this constraint there are additional constraints that you would like to impose into their system, like angle constraint, point on a curve, distance constraint, point on surface constraint, and so on and so forth. So I hope you don't get confused. But we already have a revolute joint. Let's rename it as joint 1. Okay. Now it's very important for you to know that we know revolute joint offers a single degree of freedom. And in Simscape Multibody, this single degree of freedom, it's always about the z-axis. No matter what, it's always, so if this is x, this is y, it's always going to rotate about the z-axis. Now, if you would have not changed your gravity from minus y, from minus z to minus y, then you would have to impose another rigid transform to change this coordinate system from because then your entire system would have been like this is z, and it would have rotated like this, but you want your system to be rotated, you want your pendulum to be rotated like this, right? So you would have to transform this entire rotation about this axis to this axis, and that would be very complicated. For that reason, we just changed the gravity from minus z to minus y. And now we can simply use the revolute joint because it offers you rotation about the z axis. So what we need to do is we can just double click and open it. But before that, you see there is already two frames in this revolute joint. One is the base frame and the other is the follower frame. Base frame is basically, when I talk about revolute joint, it means it will rotate with respect to something. So base frame is always connected to the point with respect to which the follower frame F is going to rotate. So that's why we have this base frame and the follower frame. So double click this. You can read about the description here, but under settings you see it only provides you rotation about the z-axis, and it has different components like state targets, internal mechanics, limits, actuation, sensing, and other things over here as well. Now, under internal mechanics, you can define the, so ideally in multibody we consider joints to be ideal, meaning they are kinematic joints and there is no wear and tear or no friction in the joint location itself. But in reality, joints are not ideal. There is some kind of stiffness and a damping, and there is some internal mechanics going on because it's like a journal bearing hub sort of assembly sort of thing. So you can define it here if you want, but we don't want it. So we want the joint to be ideal. We will keep things simple, guys. Also, in the limits, you can define the lower and the upper limit about how much this joint can rotate. I will not suggest you to do anything here. In the actuation, you can provide a certain motion actuation into the system or a certain torque into this particular revolute joint. At the moment, we are not doing anything. We are just saying that the motion should be automatically computed because everything will fall under gravity. So the motion will be determined in itself, and there is no additional torque provided to this joint. So let's not select it. Under sensing, uh, if I show you here, under sensing, we want to sense the angle of this joint. So we want to see how it is. And of course, you can sense other things as well. So the moment I press this position, and angle is a position, right, for this particular joint. The moment you press position, you see this Q port appears here. Okay, so we are sensing this. Now, under state target, we have the specific position target and velocity target. What does state target means? State target means the initial state of the system. And how do we want the initial state or the initial configuration of the system? This revolute joint, we want it to be oriented such that it is 30-degree clockwise. So what we will provide here is we will say that yes, we want a position target. We want the value to be minus 30-degree. And remember degree, not any other unit. And we want the priority to be high. So there are two priorities, high and low. Your solver over here tries to fulfill this high priority. And if you would have selected this low priority, sorry, the solver enforces to follow this high priority no matter what. But if you would have low priority as well, or if you have other systems where there is low priority, the solver will try to fulfill the low priority as well. But it will always enforces the high priority in the system. So that's why we are selecting it to be high priority, and then we simply, it's already auto apply here, right? So we simply close this and my joint one is ready. Now going back to the slide, I explained you this part already. And then let's just connect things and see how our system behaves. So I will just select this and press Ctrl R to rotate this block such that B is facing upward and F is facing downward. Just for uh, my simplicity. And you can follow the same. It helps a lot. So now I will simply uh, just go to the port or the node and just press left click and drag and select and take it to the point where I want this to be connected, right? It's showing something, just avoid that. So now my base frame of my revolute joint is connected to the world frame. So this entire thing is a world frame or the global coordinate system. Okay. Now we know that the follower uh, port of the revolute joint will be connected to F1. Very nice. Now supposedly the system, the simple pendulum should be ready. And how we can do it, how we can see if it's ready or not, there are two ways of looking at it. One is uh, from the animation itself. The second one is from the plots. Okay, if I want to see it first as a layman with the animation perspective, I can simply run and you can select the stop time the way you want it to be. It's 10 already, 10 seconds. So just simulate the model. A Mechanics Explorer window will appear. So this is the Mechanics Explorer window on your Matlab page where you so this is the current folder where your our model is saved, Simple Pendulum YouTube. Then we already have this component information here. Then obviously we have this command window here. This is the visualization window. There, this is the visual control. And what I want you to do, and this is basically the play, pause, simulation time options here. By default, Z is in the vertical direction. I want you to select this option such that Y is up. So now, the moment you say Y is up, you need to press this front view option. The moment you press front view option, you can see your pendulum, right? And of course, over here we have mechanism configuration and different properties over here. Then we have world frame. There was no property for the world frame. We have body one, the different properties you can see here. Then we have joint one and state target and everything you can see here. The same things. These are the same component blocks and the properties you can see here. If I go to the beginning of our simulation, rewind to beginning, and then zoom out, or you can press the shift button, center cursor, and you can pan, or you can press the center cursor to rotate. I don't want to rotate, I want the front view, and I want to zoom out. Then using this pan view, I'm just placing it such that I can see. And now if I select joint one, you see the joint one, the x axis of this particular body, it's at a certain angle with respect to the horizontal x, right? And this angle is basically minus 30 degree what we provided. So our body is actually starting from you see the desired angle what we wanted here to be minus 30. It's starting from that. And the moment you press the play button, you see you have your first simulating model there. So a round of applause to you if you are able to do that so far. So we started with very simple things and now we are going into more details, right? But if you follow this particular model, you'll see the simulation is not very smooth. If you want to see it in the plot also, I'll just show you quickly, okay? So this is one way of seeing if things are working fine or not. Now let's minimize this, go here. The other way of seeing it is from the plots. And how we can do that is this is a physical system and this is a physical signal. Angle is a physical signal, right? So we need a Simulink physical system Simulink converter and a scope to view it. So I will just select it, left click and drag this option here. And then right click by being on top of any one of the component and uncomment. I will name it as angle, okay? And over here also I will name it as angle, and this is PS Simulink converter, right? I'm just renaming it for my simplicity. I want this to be in the next line, so press shift and enter, and that's it. Okay. Now what you can do is, let's rearrange this and simply connect this signal to this particular block. It's very important for you to note that if the signals are not compatible, they will never connect. So that's something very good. If you would have tried to connect this particular signal to this particular block, it may not have worked. If you want to see, let me show you. So let's uncomment this. Let's delete this and try to connect this one over here. It will never connect because it's not compatible, you see, but it will easily connect here. So just for you to know, let me delete this. And let me delete the rigid transform also. We don't need it. So now if you double click the scope, you can't see anything. Because why? It's because you need to simulate your system again after you connected them. So once you simulate it again, you can see the plot. You can see the angle of the revolute joint and it's oscillating, right? But what I was telling you in before that there was some kind of uh, the the simulation to be non-smooth is because you can see here already every peak is slightly different than the other one, and the same we could see carefully in the visualization as well, right? So it's very important for you to first visualize the things and then go into the details of the graph. So that's how we did it. So what is the cause for that? Is the cause for this is the solver setting. I know you might not be experienced with the solver setting, but it's very important for you to know that the the default solver setting will work well enough for most of the cases, but it's not necessarily be the best. So what I want you to do is go to this auto and then solver setting, either from here or go to modeling, and from there you can go to model setting. press this option, it will take you to this window where you have the solver. So start time, stop time, which you already gave. Now the solver is variable step. If you can change it to fixed step, and you can change the step size, which is at the moment auto, from auto to 0.01, so which is 10 millisecond, but 0.01 is in second, right? So remember SI unit, and press OK. And now try to go to simulation, try to simulate your system again. Now if you see the animation looks much smoother. If you want, you can compare it. You can rewind the go back to the last animation that I showed in the video and then compare it with this one. But you will see. But if you don't trust me, see the plot itself. The plot now is so smooth here. You can see that, right? So clearly, by changing the solver setting, the simulation was affected so much, right? So that's very important for you to know. Now, at the same time, I'm also interested to know certain things about this body. So I could sense there was an option in the revolute joint to sense this position, right? But in the body there was no option to sense anything. So but I want to sense the so the distance in the x direction and the y direction of this particular body. How I can do it? I can do it using transform sensor. Transform sensor. So transform sensor help us to transform whatever we want to sense from a particular body, and it also has a base frame and a follower frame. So basically, when you sense something, it is always with respect to something, correct? When you were trying to sense the angle here, you were sensing it with respect to a base frame which was connected with respect to the global. So similar way, when you will sense something here, it should be with respect to something. And what would be the best reference other than the global frame itself? So we will connect the base frame to the global frame. And what do we want to sense? We want to sense, let's say, the end point of body 1, and we want to sense the x and the y directions. So meaning we want to sense uh, the global x and the global y. Or no, so we are sensing the, sorry, we are sensing the x and the y of this particular body, not the global x, global y. We are sensing the body coordinate system x, so we are sensing the body coordinate system x and the body coordinate system y with respect to the global frame, correct? Sorry about the mess here. Let me try to erase this one. Yeah, so we are sensing this one. Perfect. So we will connect this force block to F2, and we need to double click the transform sensor and let the transform sensor know what we are sensing. Are we sensing rotation? No. Are we sensing angular velocity? No. Angular acceleration? No. We are sensing translation. Yes. What translation? The X and the Y. And we just auto apply is already here and we just simply close it. So you already see a X port and a Y port. Now in a similar fashion, we can use this physical system Simulink converter and the scope to view. So you can simply select, then press Control and let your cursor be on top of any one of the component and simply click and drag. So you can see these options here. Let's repeat it. Select, press Control, be on any one of the component, left click and then drag. Perfect. Let's delete. But just select and delete. Okay. Let's rename it. So let's say this is x1. So basically, let's say this is the x component. This is the y component for the converter. Now this is the x coordinate and this is the y coordinate. Spelling mistake. Okay. Now simply connect these signals. It will be connected because they are compatible. Perfect. Now when you try to simulate again, now you can see this x co so this is x coordinate, this is y coordinate, and the angle was already there, right? So this was the angle, this is the x coordinate, this is the y coordinate. You see? Obviously you will see a smooth oscillation because that's how the system is moving. So from the visualization where it was making sense for us that the simulation is smooth, we are going into the detailed plots and that's making sense for us. Now let's go back to the slide and see if we are uh, following the slides. So I have covered most of the things from here. Then I also showed you what are the different options. Yeah, one thing that I did not show you in this particular Mechanics Explorer window is so over the visualization control here, there is visibility of frames. So the moment you press, all the frames will appear in the system. All the frames appear in the system. Then if you also press center of mass, the center of mass is also appearing in the system. There is a create video. So if you want to create, there's a video creator. If you want to create video of this animation, you can do even that. And also the shortcuts, I already explained you these shortcuts and the same you can apply it in the visualization window to apply them and see how it behaves for you. But yeah, I covered this part as well. Then I'm somewhere over here. Okay, let me show you this particular. Okay. So now we were able to visualize the results. We were also able to see the plots. But what if you want to save the plots? What you should do, the signal coming from the converter, you just need to select all the signals, be on top of any one of the signal and right click. If you right click somewhere else, you will never be able to select it. So select all the signals, be on top of any one of the signal and right click. Mm, right click and select log selected signals. The moment you do that, by default, a Bluetooth or a Wi-Fi shaped symbol will appear here. It means that now the signals are logged somewhere. And now when you press the run button again, just notice the data inspector here. Okay, let's simulate. And this glows. You see, this option is glowing now. So now when you go to this data inspector by just clicking, a window appears here where you can simply see different options here. So in my simulation simple pendulum YouTube current file, so the first run, because after logging the signal, this is my first run, right? I can see the angles here. I can see the X axis. I can see the Y. If you want to change the color, you can simply go here, change the colors, change the pattern, whatever you like. You can even play this and see how different angles and X and Y were behaving, or you can just pause it and I think there is an option of taking a screenshot. Yeah, snapshot. So whatever you like, you can do from here. And most importantly, you can save your data. You can either save this this entire data, import it, export it. So export it or import the previously saved data and so on and so forth. So you can do so many things over here, right? Also, if you simulate your system again, going back to this file, if you simulate your system again, now when you go to data inspector, sorry, this data inspector, yeah. Now you see under archive, the run one, where when we executed the first time it's here, and now I have run two. So you can even compare. So every time you execute something, if you simulate, the current simulation results will show here and the archived one will be showed here, right? So you can even compare your current simulation with respect to what you did like in the previous before changing something and things like that, and you can simply compare. So over here both are the same point because of course we did not change anything. And if you select a certain particular like signal, you can see the properties, you can rename it from here, you can change the unit and everything you can just see from the properties and so on and so forth. And by the way, the results are shown in radian. As you can see, the stored unit and the display unit is in radian, whereas for the position it's in the meters. So don't get confused, even though we provided angles to be in degree, but it's always in radian when it solves the system, just for your note. So let's go back to the slide. Now I covered this part already. Alternatively, if you want to save the data, so if you don't want to use this data inspector, you can use this. If you type, double click and type workspace, using the workspace file or using the uh, file log, I think, yeah, two files, sorry. It's two workspace or two file. Using these two component blocks, you can simply send this signal coming from this physical system Simulink converter to the workspace to basically, if you go to Matlab, to the workspace. You remember we were here in the beginning. This was a workspace. We can send your signal to be here and save it for other purposes and plot it in from the usual Matlab M file and things like that. But yeah, this was all about this slide. Now we already know how to see the animation, how to see the results, but how to analyze the results, that's very important. So as a quantitative point of analyzing the results, if we have things done correctly or not, how we can do that. But before that, let's save our file so that we don't lose data. Go to modeling, sorry, go to debug, and under debug you have Simscape. And under Simscape, there is statics viewer and variable viewer. Whenever you make any changes, always implement the change, simulate your system, and then have a look at the statics viewer and variable viewer. If you click this, it will show you the statics, the information of your system. It's opening this window. So this is my statics viewer window, and under this you need to go to 3D multi-body system, and then you can see you defined one body. Was it a rigid body? Yes. Is there any flexible body? No. There is a joint? Yes. And so on and so forth. What's most important is observe this numbers of degrees of freedom total. From our visualization, from our logical sense, we know that this simple pendulum in space will have 1 degree of freedom. Very good. From our mathematics in the beginning, I told you that even in 3D, there will be 1 degree of freedom, right? Exactly the same information you can see that your system is 1 degree of freedom and there are no redundant constraints. Number of position constraints, non-redundant, 0. There are no redundant constraints, so everything is fine here. Perfect. Now just close this. I don't know why it's not getting closed. Anyways, let's go back to debug Simscape, and now it's taking time. The system hanged for some reason. Mm, Nothing is working. Okay, what I would like to show you here, uh, if you go to debug, then Simscape, the system has hanged, guys. Anyways, let me show you it in the slide. If you go to Simscape variable viewer, you will see a window like this, where you will see information about the different variables that were used, and the variable that you are using is the joint angle and the joint velocity. We did not provided any state target for the joint velocity, so there were none, but we provided a state target for the joint angle, which was minus 30 degree, and the priority was high. So when it says at the start it is minus 30 degrees, so things are starting as it should be, and the status you can see it's in green, so things are fine. Also, if you go to diagnostics, you can see everything is fine there, but if there would be some problem, it will appear already in the diagnostics. Okay. Yeah, now it's closed. Actually, I can actually go. Still no. I don't know what's wrong. So everything has hanged. Okay, I'm not able to do anything. I'll just pause the video and I'll resume recording. Okay. It's working now. Okay, it's working already. So go to variable viewer, and under variable viewer you can see the same information I said, and under diagnostics all targets are satisfied, so everything is fine. Just close this, just for you to analyze the results. Now going back to the slide. Yeah, so now when things are fine for a simple pendulum, all we can do is just use the best technique that we engineers follow is a copy paste technique, and we can use that copy paste technique to just model a double pendulum. How we can do that? So I would really so you have already saved this like as a simple pendulum. Wait a minute. I think there is internet issue at my place. Yeah, it's connected. Yeah, it should work fine. So you guys have already saved it as a simple pendulum. You can go ahead and save as a new file naming double pendulum. Why? It's because now we are just extending this simple pendulum to be a double pendulum. How we can do that? Let's scroll out, like zoom out, I mean. Things are hanging now. I'll just close these windows, okay? I just want to show you this one. Scrolled out, zoomed out. I want to copy the first body, the joint one, and everything associated to that in order to sense things. So I just carefully select B on any one of the component, then press Ctrl and left click and then drag. Correct? So now let's rename everything. So obviously this is joint 2, this is body 2, this is transform. It should be transform 2 actually. Things are hanging in my system. Sorry guys. Yeah. So this is transform 2 actually. And this is transform 1. Let's rename the first one as well for simplicity. Renaming is very important. It will make your life easy. So earlier for body 1, let's say this is angle 1. This is angle 1. This is basically x1. Just renaming for the first body itself because now we have two bodies, right? My system is hanging big time. Just have to be patient. Okay, this is y1, y1. Now this is angle 2. This is angle 2. Now this is x2. This is x2 coordinate. This is everything is hanging. This is y2. This is y2 coordinate. And that's it. I think all the naming is done correctly. Yeah, all the naming is done correctly. Now we simply need to go ahead and start just connecting things. Okay. So if you see here, now just we copy pasted the same thing to be here. And now my F1 of the second body is here. And that needs to be connected to F2. So basically this joint needs to be connected to F2 of the first body, right? So what we will do, let's zoom in. So this base frame of the revolute joint needs to be connected to F2, correct? So now it's connected to F2 here. Perfect. And the base frame of the transformer still needs to be connected to the global coordinate system. So this is the global coordinate system line and it's connected to that already. Now, if you want to adjust certain parameters, you can already do that. For example, I want my body 2 to be different in color. So I double click this body 2. Sorry about the hang, guys. Yeah. So my body 2 here, and under graphics, I just go to visual property. This is red, green, and blue. I increase the green value. Now, I keep the red value as it was 0.5, increase the green value from 0.5 to 0.9. Press enter and then update the visualization window and press OK. So now my body 2 is green in color. Also note, joint 1 had a certain position target which was minus 30 degree with respect to the global frame. If you want, you can take that state target away in joint 2, but I'm saying let it be there because what will happen is this was at an angle 30 degree clockwise with respect to the global one. So now this body also, if you see this particular body green, it is also, this is the x, okay, this is the y. This body also is at a certain angle. So this angle, so you see basically if I extend this angle is also 30 degree clockwise because we have the same state target there, right? So where is it gone? Okay. So it will behave in a similar fashion. Okay. Very important to save the model. I hope I'm able to save the model with all the problems that I'm facing right now. So basically technical fault which I have no idea about. Okay, now just go ahead and save the file. It's asking me so unable to save let me save as. Let me save as in some other folder in the downloads maybe. Okay, and I just try to save it here. Why this problem was appearing is because I always try to work on some public folder network that we work here in our offices. So that folder is not accessible at the moment. But I used the same name. I could have just changed the name to be Double Pendulum YouTube, right? But it's fine. But you will be asking, do I need to change the folder even here? Yes, it will. You would need to change the folder even here because at the moment it's not able to access this. So go to browse folder. Things are hanging big time. So it was already showing me warning in the command window that there was some problem. So I just selected my download folder, which is fine. Right. I'll just pause this video. I'll see what is the problem that I'm facing and I'll resume recording, okay? Ah no, it's back. So I'll just select the folder. Every time I say this, things start working already. Okay. So now go back to my simulation and simply run the simulation and see how does it behave now. So now if you zoom out, you can see already that there is a double pendulum. If you see from the beginning, this angle, this body is at a 30-degree angle clockwise. Similarly, the green body is at an angle 30-degree with respect to the first red body. And the moment you simulate, you can see what's happening there, right? So at least our model looks in good shape, and if you want to rotate and see how things are, you can still see the 3D animation. It's little weirdly, yeah. So the way you want to see it, it's up to you. Correct. Perfect. The same things you can see in the plots here, in the angles here. If you double click, you can see the angle, the positions, and so on and so forth. But let's go back to the slide. Yeah, so you always save your model at every step, like I said you, because I faced some problem, you might face something similar. So now we already saw an animation like this, and we already saw some analysis as well, but from the technical point of view. But it is very important to analyze the plots that you see onto the screen. So the plots that I just showed you, these plots, if you are unable to analyze it, it doesn't make sense. I always believe that anyone can model a system, but not everyone can analyze the data in the most effective way. Whenever I try to model anything, even now, I always try to relate that how my modeling or how I can analyze my model so that it can be useful to a layman, or I'm able to make a layman understand uh, the outcome of it, like an executive summary. Because not everyone can understand engineering at the first place. And remember that science must be used to make life simple and not complicated. So remember, we start with simple approach that we want to model a double pendulum. Let's subdivide the requirements that we need to have. When we had the requirements, we went on to fulfilling those requirements one at a time. Now, when everything was working, we went into the more details and analyze and saw the results, the animation. But now we want to come up a step backward, that how the same things can be analyzed in a most in the simplified form. Of course, I went ahead and further experimented the model, and I saw that by providing different initial angles to this particular first body or the second body or both of them, the system behaved completely different. So there was a very sensitive dependence. The entire system has a very sensitive dependence on the initial condition of the model itself. So I concluded that a double pendulum undergoes a chaotic motion. And this kind of analysis, even anyone can understand what is a chaotic motion. Nothing in order is a chaotic motion, right? So what I mean by that, let's see it in this video. Always remember to analyze your results, your plots in a simplified form. And that kind of approach is the right approach, whether you are in the research line, whether you go to a company, anywhere, because a CEO won't understand the technical details. He would just like you to make an executive summary, right?
Älä paina torkkua unelmillesi, sillä tavoitteet on tehty saavutettaviksi. Arla-proteiinrahkojen avulla saat energiaa päivääsi ja uusien haasteiden kohtaamiseen. Jaksat aina yhden askeleen ja toiston enemmän. Nyt myös uutuusmaku päärynä kaupoissa. Tankkaa tahdonvoimaa.
I don't know if you are able to follow the music along the video, but I will make the link of this video available in the description of this video. So even if this says that it is chaotic because it is highly sensitive on the initial condition. So a tiny change will result into a different motion altogether. What I was trying to say, just see this animation. So there are different initial conditions given to the second body, and now see the behavior. This looks so beautiful. See, if you can use science to do something like this, perfect. Your job is done as an engineer. So this is what I was trying to say. Every single trajectory is different. No two of them follows the same trajectory at all. Right? So that's what I was trying to explain you here. So now let's go back to the slide. So I have certain suggestions that if you have reached so far in the tutorial already, it is highly recommended that you should read the official documents from Simscape Multibody. So this particular link, which will also be available in the description of this video, and it will provide you much better explanation than what I did here. But yeah, I tried to explain you as simple as possible. I hope the message was conveyed. But even if after all of this you end up in some error, please read the error or the warning or the error message before doing anything, and try to understand what it is saying. Sometimes the error message itself gives the problem in such a descriptive form that you are able to solve it. But try to solve, if there are so many errors, try to solve your problem one at a time and step by step. Do not try to do everything at once. One step at a time, and take baby steps. And whenever you are trying to model, try to reuse the old models or the parts that you already have modeled it before, but with extreme care. Extreme care as in what needs to be changed when you are reusing those models, you need to be very careful about that. Remember that automatic solver selection is not always the best solution. Okay, and choosing the solver and its setting, it's not always simple as well. You need to be very careful with choosing the solver setting itself. But remember, a correct solver will help you to get accurate results with good performance, and an incorrect solver will not give you accurate results. If you want to read more about these topics, about different not different integrators, but how the integrators are made, or how the simulations are made from scratch, or what are the governing equations behind that, you can read one of my paper here. It's not obligatory, but if you want to read and try to learn how research is done at the first place, feel free to do that. Okay. And again, this is taking a lot of time to open, but I will provide the link in the description of this video, okay? But let's go back to the next. Okay, it's already opening. It's taking a lot of time. It's okay. I'll provide the link. But with that, thank you so much for following this video and this tutorial. If you have any questions, please comment your questions in the comment section of this video. And for in-class students, please, if you have any questions, you feel free to just email me. I think in the lecture from Professor Akimikola, you can already get my email ID already. And if you want to visit me in my office, you can do that as well. With that, thank you so much, and do subscribe to the channel for more interesting videos like this, and have a good day. See you.